Ladies and gentlemen, my name is Zhang, and I come from Space Star Technology Company. The title of my paper is LEO Assistant Beidou B1C Signal Acquisition Algorithm and On-Orbit Verification. My paper consists of 5 parts: Introduction, System Model, Algorithm Model, On-Orbit Verification, and Conclusion. Chapter 1 Introduction. In practical applications, GNSS navigation signals are widely used in weak signal environments, including urban indoors, forests, mountains, underground garages, and so on. The carrier-to-noise ratio CNN of satellite signals in these environments is about 15 dB lower than that in an open outdoor environment. The aggregation sensitivity of traditional receivers is difficult to meet the acquisition requirements of weak signals in these complex environments. In view of the shortcomings of the direct acquisition method, this paper proposes a LEO-assisted Beidou B1C weak signal acquisition algorithm through the LEO satellite to obtain code phase estimates and Doppler estimates to extend the coherent integration time, improve the weak signal capture ability. Chapter 2 System Model. First, this paper analyzes the advantages of LEO satellites. The orbital height of LEO satellites is lower, which is about 5% of that of conventional GNSS satellites. The free propagation loss of the signal is small, so the signal received on the ground is stronger. The LEO satellites are faster, the Doppler change is faster, and the geometric pattern changes quickly, which is conducive to the use of Doppler for positioning. The research and development cost LEO satellites and rocket launch costs are relatively low, and they can be launched by multi-satellites with one rocket. Then this paper designs a LEO navigation enhancement system. LEO navigation enhancement system includes GNSS constellation, LEO satellites, and ground navigation enhancement terminal. GNSS constellation transmit GNSS navigation signals. LEO satellites broadcast navigation enhancement signals forward the ephemeris of Beidou satellites. The ground navigation enhancement terminals complete course positioning and timing by the LEO satellites independently, and accurate positioning and timing services by BDS satellites and the LEO satellites. Chapter 3 Algorithm Model. Section 3.1 BEC Signal Model. Signal structure. Compared with the BPSK single-channel signal system of Beidou 2 and the Beidou 3, BEC signal adopts a new bulk modulation method, and at the same time, it has also been improved from a traditional single data channel to a data and pilot dual channel structure. The data channel modulates a navigation message containing ranging information, while the pilot channel does not contain any data information. The baseband signal expression is as follows. Ranging code structure. The BEC ranging codes are the tied codes, which are generated by primary codes with secondary codes. The chip width of the secondary code has the same length as one period of a primary code. The start of a secondary code chip is aligned with the start of the first chip of primary code. Section 3.2 Algorithm Design. This paper, because the data and pilot components of the BEC signal are synchronized, so this paper captures the pilot component. This paper uses the assistance of the LEO satellites to extend the coherent integration time as the main method, and the non-incoherent as a supplementary method to capture BEC weak signal. There are 5 steps to perform the algorithm. The first one is course positioning and timing. The ground navigation enhancement terminal uses the LEO navigation enhancement signal to independently complete course positioning and timing, and at the same time obtain the retransmitted ephemeris of the visible Beidou satellites. And the second is Doppler and code phase estimates. According to the results of the course positioning and course timing and the transmitted ephemeris of the visible Beidou satellites, considering the receiver clock, offside clock, drift, and other facts, the Doppler and code phase estimates of the Beidou visible satellites are calculated. The third is frequency search. The ground navigation enhancement terminal uses the Doppler estimate to reduce the frequency search range when searching for frequencies. Primary code phase search. The ground navigation enhancement terminal uses the code phase estimate to reduce the primary code phase search range. And the last one is strip secondary code. Using the code phase estimation value, the secondary code is stripped and performing long-time long-term coherent integration. Section 3.3 Determination of integration time. Considering facts such as frequency errors, search step length, and dynamic performance of the receiver, noise, and so on, this paper uses 18 milliseconds coherent integration time and 2 non-coherent integrations to capture. Chapter 4 on Orbital Verification. Section 4.1 Testing Platform. In order to verify the effectiveness of the LEO Assistant BEC acquisition algorithm for improving the anti-jamming performance, this paper carried out an on-orbit test for experimental verification and analysis. The equipment required for the ground test verification platform mainly includes GNSS and LEO receiving antennas, anti-jamming navigation receivers, interference generators, companions, computers, and so on. Receive and process navigation signals. Computer displays the test results and stores the test date. Antenna receives GNSS navigation signals and LEO navigation enhancement signals. Jammer generator interference signals. Combine the signal received by the antenna with the interference signal. Section 4.2 Testing Process. The design of the test process is mainly to compare the anti-jamming ability of interference and non-interference scenarios. See the paper for details. Section 4.3 on Orbital Test and Results. On December 9, 2020, in Beijing, China, a ground receiving test was conducted on a LEO satellite signal in orbit. The visible time range of the LEO test satellite is 514 seconds. LEO signal power test. Normally and continuously, LEO signals were received within the visible time. After successful acquisition and stable tracking, as shown in the Figure 5, the satellite's elevation angle to the ground varies from 9 to 35 degrees, and the statistical ceiling is from 14.7 dB to 16.3 dB. The ceiling of the Beidou satellite is generally between 13.7 dB to 15 dB. It can be verified that the ceiling of LEO is about 10 to 20 dB higher than that of GNSS satellites, which is feasible for assisting BEC weak signal acquisition. Then test anti-interference ability. The results are shown in Table 1 and Table 2. In the non-interference and the anti-interference ability of the normal acquisition model is 28 dBc. This is RSR equal 28 dBc, and in the interference scenario, the anti-interfere ability of anti-interfere acquisition mode is 14.2 dBc. It shows that the anti-jamming performance of the LEO-assisted BEC acquisition algorithm proposed in this paper is very effective. The on-orbit test shows that the anti-jamming ability of the LEO-assisted BEC acquisition algorithm is improved by 14 dB. Chapter 5. In summary, this article analyzes the vulnerability of GNSS and occlusion and interference environments, and compares the effects of coherent integration and incoherent integration on the signal processing gain. This paper designs a LEO navigation enhancement system and proposes a LEO assisted BEC acquisition algorithm, and analyzes the effectiveness and feasibility of the LEO assisted acquisition algorithm from various aspects, such as system design and algorithm principles. Through the on-orbit test analysis of an on-orbit test satellite, it is obtained that the anti-jamming capability of the BEC signal with the assistance of LEO can be increased by 14 dB, which is of great significance for improving the anti-jamming performance of the GNSS signal. So, thank you.